Hello everyone, welcome back to my channel. Today we'll be solving the chemistry HL paper of the November 2022 attempt. So let's start with the first question. In this question, we have to find the number of oxygen atoms that are present in 0.05 moles of hydrated barium hydroxide. So first I'll find the number of molecules of barium hydroxide in this 0.05 moles. We'll find that using just the formula. We just can multiply the moles of the compound with the molar mass. We'll get the number of molecules. So molecules of BaOH whole twice dot 8H2O. This will be 0.05 times Na, right? Yeah. Now we have to find out how many oxygen atoms are present in one molecule of this barium hydroxide. So if I calculate this, see, in the BaOH whole twice, in this portion we have two atoms of oxygen, and in 8H2O we have 8 atoms of oxygen. So 2 plus 8, we have 10 atoms of oxygen present in one molecule of barium hydroxide. So number of oxygen atoms present in one molecule of hydrated barium hydroxide, this will be 10. So in each molecule of barium you'll have 10 molecules, 10 atoms of oxygen, right? So how many number of oxygen atoms will be present? This will be number of molecules of barium hydroxide times 10. So number of oxygen atoms in 0.05 mole barium hydroxide would be 10 times the number of molecules of barium, that is 0.05 Na. So that will be 0.5, and the value of Na is given here, 6.02 times 10 to the power of 23. If I simplify, I'll get 3.01 times 10 to the power of 23. So if I look at the option, that corresponds to option A. So we can say option A is the correct answer to this question. Moving on to the question, what is the change of state for a gas to a solid? So we have four options. Condensation. Condensation is basically conversion of a gas to liquid, so that can't be our answer. Deposition. Deposition is the correct answer here, because this deposition is a conversion of a gas to a solid. So option B should be the correct answer here. If we go through the other options, freezing is obviously a conversion of a liquid to solid, and sublimation is a conversion of a solid to gas. So yeah, option B should be the correct answer to this question. Moving on to question 3, how many moles of carbon dioxide are produced by the complete combustion of 7 grams of ethene? So this is a typical stoichiometry question. First, we have to find the balanced chemical reaction of combustion, right? So C2H4 plus O2, this will give us CO2 plus H2O. These are the products of a complete combustion. So if I try to balance this, we'll have 2 CO2, 2 H2O, and I can just put a 3 in front of the oxygen, and I hope this balances the reaction. Yeah. So the reaction is now balanced. Now we have to apply the stoichiometry. First, let's calculate the moles of C2H4. Moles of C2H4 is given mass. It is the given mass divided by the molar mass. So 7 divided by 28, that will be 0.25. These are the moles of C2H4. Now we have to find the moles of carbon dioxide. So I'll be applying the stoichiometric ratio between C2H4 and CO2. I can write the ratio as moles of CO2 produced by moles of C2H4 reacted. This will be equal to 2 by 1. Now, moles of C2H4 reacted, we would assume that all of the C2H4 has been reacted. There is no, there is none of the ethene left. So I can just write, put it in this formula like this: moles of CO2 produced divided by the moles of C2H4 reacted would be the total amount, that is 0.25. This will be equal to 2. So from here, moles of CO2 produced would be, this will be 2 times 0.25. That is basically 0.5. So from the options, option B is the correct answer to this question. Moving on to question 4. So these are the successive ionization energies of an element. So what energy in kilojoule mole is required for the element to reach its most stable oxidation state in ionic compounds? Now first, in order to do that, or in order to find the energy, we have to find out how many electrons are there in the outermost or the valence shell of this element X. So here we see that the biggest jump in the ionization energy occurs between 2 to 3. From this, we can have an idea that there are 2 electrons in the valence shell of this element, right? And if we could successfully remove both of these electrons, our element X will be in its most stable oxidation state, that is X2 plus, right? So what would be the total what would be the energy required? So that will be the total ionization energy. You can write it in thermochemistry stuff. So this is the first. With this, the first electron is removed, and from M plus I can remove the second electron. Delta H in this case will be 1450. Now if I add up these two reactions by Hess law, I'll have M giving you M2 plus 2 electrons, and the total enthalpy change of this reaction will be 1450 plus 740. That will correspond to 2190 kilojoules of mole inverse. So this would be the total energy required to remove both the electrons from this element X, right? I have written M here, so but it will be actually X. So yeah, from the options, option C is the correct answer to this question. Moving on to the next one, so we have been given two species. This is tellurium and iodine. So we have to find which quantities are different between these two species. From the options, we can see that we need to compare between the number of protons, neutrons, and electrons, right? In TE, in TE 12852, number of protons will be 52, equal to the atomic number. This is a neutral species, so number of electrons will also be 52, and the number of neutrons will be 128 minus 52, which basically gives us 76. For iodine 12853, number of protons would be 53, that's equal to the atomic number. Number of electrons will be 53 plus 1, because there is a negative charge. Negative charge means we have one electron greater than the number of protons. So that will be 54 here, and the number of neutrons will be 128 minus the number of protons. So simplifying, this will be 75. So you see the number of protons are different, number of electrons are different, and the number of neutrons are different. So all of these three quantities are different, and as we know, option D is the correct answer to this question. Now part 6, which explains why complexes of D block elements are colored. This is like a classic explanation. What happens is D block elements will absorb specific wavelengths from your visible light to get to jump to a higher energy orbital. And since only a specific wavelength of light is observed, the rest of the visible spectrum will be transmitted. As a result, the transmitted light has a complementary color to the absorbed color, and that's how D block elements get their color. So I'll write the explanation here. D block elements absorb specific wavelengths of light from visible light to jump. If I want right to jump, and hence the electrons could jump to a higher energy orbital or higher energy orbit, both of them will be fine, since only a specific wavelength is absorbed. The rest of the visible spectrum is transmitted. And as a result, the transmitted light has a complementary color to the absorbed frequency, or to the absorbed you can say frequency or wavelength. So from this information, we see when light is absorbed, when electrons are promoted to between d orbitals. Option A is the correct answer to this question. Moving on to the next one, which elements are considered to be metalloids? So I write the list of metalloids, that is boron, silicon, germanium, arsenic, antimony, and tellurium. So these are our like 6 metalloids in the periodic table, and out of them we see germanium and arsenic in the options, that is 2 and 3. So option C is the correct answer to this question. These two. Moving on to the next question, which property of elements increase down a group but decrease across a period? Okay, if I go by the options, atomic radii definitely increases down a group, because when you go down a group, more and more shells are being added to the elements. So as a result, the atomic size will increase. And if you move left to right across a period, the the nuclear charge will increase. As a result, the atomic radii will decrease. So from here, I can definitely say option A is the correct answer to this question. But we can also check option B and C. For electronegativity, electronegativity will decrease down a group and increase from left to right of a period, right? So that will not match with the condition that's given here. Ionic radii will increase down a group, but across a period there is no specific order. That in some part you can say it increases, then it decreases, and also ionic radius will also not fit into our condition. And ionization energy decreases down a group and increases across a period. So option D will not fit in our condition. So from this, option A is the only possible answer. Moving to the next question. So which molecule can be represented by resonance structures? So here, in order to understand this, just remember 2 conditions which we look for resonance. Okay, the first condition, you should have a lone pair or negative charge in conjugation with pi bonds, or in conjugation with double bond or triple bond. So this is the first condition. Second condition is you can have a positive charge and a pi bond in conjugation. Now we have to look through the options. Option A, H2S. H2S when dissociates forms H plus and S2 minus signs. So there is like no bonds in both of these signs. So H2S cannot be our answer. HNO3 when it dissociates forms H plus and NO3 minus signs. NO3 minus, if I wish to draw this, the Lewis structure will somehow look like this. 3 oxygens, right? So yeah, this will be the Lewis structure of NO3 minus. So in this Lewis structure, we see that we have a negative charge and a pi bond which are in conjugation with each other. As a result, this will show your resonance structure. So what happens is a double bond, lone pair can come here, form a double bond, and this double bond can open. As a result, this could be one of your resonance structures. Minus 1, 2, 3, 4, 5, 6 minus, and we can also have this resonance structure. Well, this lone pair. I'm talking about this lone pair, not the charge. Sorry, yeah. This lone pair will jump and form a double bond here, and this double bond will open up. As a result, you can have this resonance structure. So from this, we are pretty much sure that B would be our answer. We can also check C and D. H2O2 has a structure which looks like this. So there is no pi bonds, or there is no, there is no pi bond, so there will be no resonance structure here. And about HClO, it will look like this. Yeah, HClO will dissociate to form H plus ion and ClO minus ion. So this is ClO minus. Also here you won't find any double bond or something, so that you could draw resonance structure. So from all of this, we can say option B is the correct answer to this question. And yeah, HClO will look like this. O and hydrogen will have a bond. The next one, which elements are capable of forming expanded octets? So for this, there is just a simple rule. Any element which is in period number 3 or greater than that can form expanded octets. You should have electrons in n equals 3 or more, so that these elements can expand their octet and use the d orbitals which are available. So here nitrogen, we know nitrogen is in period 2, like the last valence electron is in period 2, so nitrogen won't be able to form expanded octet. Phosphorus is in period 3, while arsenic is in period 4. So from here we can see phosphorus and arsenic are the only two elements here which have electrons in n equals 3 or more, right? So yeah, from all of this, we can only say 2 and 3 can form elements with expanded octets. That would be option C. So option C is the correct answer to this question. So starting with the next question, we have to identify which molecule has a tetrahedral molecular geometry. So in this question, we'll be applying our general concept, right? So for HNO3, we know that the structure will look something like this. I'm so sorry for that, yeah. So N plus. So around nitrogen, there are 3 electron pairs, right? 3 atoms attached to nitrogen, and there is no lone pair. So in this case, what happens is, like, we can max have a trigonal planar molecular geometry, but it won't be tetrahedral. For the next one, SF4, first we'll find a number of electron pairs around S. This will be half times the number of valence electron in sulfur, which is 6, plus the number of monovalent atoms attached to this sulfur atom. So number of monovalent atoms, that is the 4 fluorine. So fluorine always makes a single bond with sulfur. So this will be 5. Number of lone pairs around sulfur. This will be total number of electron pairs minus the number of sulfur atoms attached, minus the number of fluorine atoms attached to the sulfur. So number of lone pairs will be 1. So in this case, if you have 5 electron pairs and 1 lone pair, we know that the molecular geometry will be seesaw. Okay. So the electron geometry will be trigonal bipyramidal, and the molecular geometry will become seesaw, as there is 1 lone pair around the sulfur. So this cannot be our answer. Next one, if I move to C, that is XeF4. So first we need to find out the number of electron pairs around Xe. This would be half times. Xe is a noble gas, so it has 8 valence electrons. Plus it has 4 monovalent atoms, or 4 fluorines attached to it. So this will become 6. And the number of lone pairs around Xe, this would be 6 minus the number of fluorine atoms attached to it, that is 2. So if you have 6 number of electron pairs, the electron geometry will become octahedral. And if you have 2 lone pairs, then the electron geometry, the molecular geometry will simply become square planar. So here this will be square planar. And if I check part D, XeO4, again number of electron pairs around Xe. this will be half times the number of valence electron on Xc. There is no positive, there is no negative charge, there is no monovalent atoms attached to Xc. Xc is attached to oxygen atoms which are not monovalent. Oxygen will form double bonds with Xc. So the number of electron pairs will just be 4. So if the number of electron pairs is 4, then we can say that the electron geometry is tetrahedral. Now we need to check for the molecular geometry. Do we have any lone pairs around Xc? So lone pairs around Xc. This would be total number of electron pairs is 4, and we see there are 4 oxygen atoms attached to it. So lone pair would be 0, right? So if the lone pair is 0, your electron geometry becomes same as the molecular geometry. So so your molecular geometry will be tetrahedral in this case. So checking all the options, option D is the correct answer to this question. Moving on to the next part. Allowing a metal with a metal of a smaller atomic radius can disrupt the lattice and make it more difficult for atoms to slide over each other, which property will increase as a result. So when we talk about sliding, it's always about the strength, right? So I can clearly or just say that the strength will be affected. But what's the exact reason? So let's look at the reasoning. So the thing is, let's say you have, these are the big or the normal atoms of the lattice. I'll just try to draw them quick. 2, 5. And let's say these are the smaller atoms from the in the alloy. Just draw them a little bit bigger. And this is one case, and in the other case, let's say we have the metals without these small atoms. Sorry for that. Yeah, we can just draw 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now if I apply a shear force on this, let's say there is a shear force here. In this case, what happens is the molecules will slide over each other. There will be this much sliding. But if we apply the shear force again in this in this configuration, what happens is there will not be much sliding. So I can say 1, 2, 3, 4, 5. These are the small atoms of the elements. Yeah, 2, 3, 4, 5. So as a result, what happens is the strength of the metal will increase. Now the ductility, malleability, or the electrical conductivity might also change if you create an alloy, but again that will depend upon the amounts of the two metals that you have mixed, the properties of the two metals. But yeah, if I just check about, if I just go through this information, that is smaller atomic radius can disrupt the lattice and make it more difficult for atoms to slide over each other, it will always be strength. So what happens is the strength of this metal or strength of this alloy will increase. Moving on to the next question, we have chlorofluorocarbons which contain these bonds. So we have to arrange these bonds in the increasing bond strength. To solve this, there is just one information which we need to know, that is bond strength is inversely proportional to the bond length. Right? So I can say shorter the bond length, greater will be the bond strength. So yeah, so among these three, CF bond has the shortest bond length. So CF will be the strongest bond. So CF will be on top, so either it will be option B or C. After CF we have CC bond and then CCl. So CF, CC, CCl. Option C is the correct answer to question 13. Moving on to question 14, this is a typical Hess law problem, right? So here we have to find the enthalpy of formation of methane. So first write the required reaction. We need to find the enthalpy for this reaction. That is C solid plus twice H2 gas gives you CH4 gas. This is the enthalpy of formation of methane reaction. We need to find the delta H of this reaction. Right? And we are given these three reactions. So how will I construct, or how would I construct this reaction using these three reactions? So the method is pretty simple. Like see, as C is on the left and C has a coefficient of 1, I'll just keep C as it is. So the first reaction will go as it is. So C solid plus O2 gas. This will give you CO2 gas. Delta H will be minus 394. In the second one, we see there is H2 plus half O2 giving you H2O. But in our reaction, we have twice H2. So I'll multiply the second reaction with 2. So twice H2 gas plus O2 gas gives you twice H2O liquid. The enthalpy will become minus 286 times 2. And in the third equation, we see that CH4 is on the right hand side in our equation, but in the third equation, CH4 is on the left. So I'll just reverse the equation. So it will be twice H2O liquid plus CO2 gas. This will give me CH4 gas plus twice O2 gas. Delta H of this reaction would be, if we reverse the reaction, the sign of the delta H will change. So it will be 891 kilojoule per mole. right? If I add these three reactions up, see these these will get cancelled. So CO2 gas will be cancelled from both sides, H2O liquid will get cancelled, we have 2 oxygen on the right, we have 2 oxygen on the left, this will also get cancelled. So finally I'll be getting the same reaction as our required reaction, right? So I can say the delta H will be sum of these three delta H's, so that is minus 394 minus 286 times 2 plus 891, and the unit will be kilojoule mole inverse. As it's paper 1, we don't need to simplify this. So if I check the options, I personally think, yeah, it's option D is the correct answer to this question. Now moving on to the next part, which magnitudes of lattice enthalpy and hydration enthalpy of ions for an ionic substance would result in the most exothermic enthalpy of solution? The thing is, here we need to know the concept of lattice enthalpy. Okay, lattice enthalpy and your hydration enthalpy. So lattice enthalpy is basically endothermic, because it is the energy that is required by the ionic compound to break the 3D lattice and to get dissolved in water, right? So obviously if energy is required, so water has to supply this energy to the ionic compound, so hence lattice enthalpy is endothermic. Just make a point here, lattice enthalpy is endothermic, as it is the energy required to break the 3D lattice of an ionic compound or of an ionic solid, right? And in the second part, the hydration enthalpy, I would say the hydration enthalpy is exothermic, because hydration enthalpy is defined in such a way that it is the heat energy released when new bonds are formed between the ions and the water molecules. Like thing is, hydration enthalpy is always exothermic, because if you try to dissolve an ion in water, ion and the water molecules, okay, so water molecule is polar, ion is an ion, so there will be an ion dipole interaction. So if an ion dipole intermolecular force of attraction starts to exist, what happens is the system becomes more stable and some heat will always be released. So hydration enthalpy is always exothermic. I would say hydration enthalpy is exothermic, as it is the heat energy released when new bonds are made between the ions and water molecules, right? So hydration enthalpy is exothermic while lattice enthalpy is endothermic. So if I want a net exothermic enthalpy, right, net exothermic enthalpy, I want the exothermic reaction, the magnitude of exothermic enthalpy to be high and the magnitude of endothermic enthalpy to be low, right? So that's why I want the magnitude of lattice enthalpy to be small and I want the magnitude of hydration enthalpy of ions to be large. So from this I can say option C is the correct answer to this question. Now moving on to the next question, we have to find out which alkane has the lowest standard entropy, right? So for entropy we can actually compare with 3 points, right? First is the internal energy. What is about the internal energy? See, internal energy is a function of the molecular weight. Greater the molecular weight, greater will be the internal energy. So if there is a greater internal energy, we can say that the vibrational energy will also be greater. So C4H10 of the bigger molecules will vibrate faster or vibrate with a number of different vibrational states or orientation. So the randomness, I can say from here that the entropy will be greater for like bigger molecules, because they have greater vibrational energy and greater number of vibrational states. So I can just say, just write it here in short, internal energy increases with increasing molar mass. Hence, vibrational energy also increases. And as a result, entropy increases. Other than this, there are 2 more logics you can apply. So as we go down, the number of atoms also increase. CH4 has 5 atoms, C4H10 has 14 atoms. Okay, I can say increase number of atoms. So basically, if the number of atoms are increased, what happens is the number of ways in which these atoms can be arranged in 3D space can also increase, right? And hence there will be an increase in entropy. So this leads to an increase in the number of ways in which the atoms could be arranged and hence increasing the entropy. There can be also one reason, that is increased molecular complexity. So what happens is, if you have bigger molecules, right, bigger molecules will have a number of possible configurations and orientation, so which can increase the entropy. So I can say bigger or more complex, or say more complex molecules can have a number of possible orientations, possible configurations and orientations. And which in turn will increase the entropy. So from all this information, we know one thing, that C4H10 will have the highest entropy because it has the highest molecular mass, right? It has the highest number of atoms. It also has the most amount of molecular complexity. And CH4 will have the lowest standard enthalpy. Why? Because it has the lowest molecular mass, so lowest internal energy, lowest number of atoms, and the lowest molecular complexity. So from all this, we can say option A is the correct answer to this question. On to the next question. At which temperature could delta H, delta S and delta G would all be positive? So here we would assume that delta H and delta S are already positive, okay, because these are reaction and the the molecule dependent. So delta G we know is delta H minus T delta S, right? So here we know that delta S is positive and temperature T is always positive because T is always taken in Kelvin, and Kelvin starts from 0 Kelvin and keeps increasing. So this T delta S is, this entire term is positive, and delta H is positive. If in case delta H is greater than T delta S, your delta G would be positive. If delta H is less than T delta S, so your delta G will become negative. I want delta G to be positive. Okay, so I want this delta H to be greater than T delta S, or I want this T delta S to be as small as possible, so that delta H is greater than T delta S, right? So if I want T delta S to be as small as possible, see, delta S is already a fixed quantity, I can't change that, but if I have a low temperature, what happens is the product T delta S will become less, and as a result the delta G will be positive. So here I'll be looking at a low temperature, so T will be as low as possible. So option B is the correct answer to this question. In question 18, we have to find the initial rate of the reaction. So here what we have to do is, first we have to more or less plot a curve. I've already done that, and we have to draw a tangent at the initial point. Okay, initial point means at T equals 0, wherever the curve is, you have to draw a tangent at this point. So here you can do it with a pencil and a ruler. You don't have to be like really accurate with this, because even if your line isn't accurate, your answer would be, you'll get an answer in a range. So here just remember, the negative of this slope will give you the initial rate, right? Because this is the concentration of the reactants. So initial rate would be negative of the slope. So slope is delta y by delta x. Delta y is initial, minus of initial final concentration of y is 0. Okay, final concentration is 0, initial concentration is 1.6. And in this line, the time, final time is 12 seconds, initial time is 0 seconds. So if that will be 1.6 by 12 if I simplify, and if I simplify it again, I'll get approximately 0.133, which can be rounded off to 0.1, and the unit unit of rate will be mole dm cube second inverse. So 0.1 mole dm cube second inverse would be the answer, which corresponds to option A. Moving on to the next question, which changes would increase the rate of exothermic reaction? So first thing is, for an exothermic reaction, if we increase the temperature, the rate of reaction will increase. This is like an information which you need to know. Rate of endothermic reaction increases with increasing temperature. And the particle size. Now thing is, if you make the particle size smaller, the rate of reaction will increase irrespective whether it's exothermic or endothermic, right? So we would always prefer a smaller particle size. The rate of reaction will increase if we have a smaller particle size. And this is irrespective whether your reaction is endothermic or exothermic. So comparing these two, we need greater temperatures and smaller particle size. So option A is the correct answer to this question. Moving on to the next question. This is a classic question. Every year a question like this turns up in the IB papers. So yeah, So we have x2, y2 and the rate. So we have to find the rate equation from this, from the concentration and rate data. So these, I mean, I'll assume them as the initial concentration and the initial rate. Now, if I double the rate of x2, okay, the rate becomes 4 times. So from this, I can say that rate is directly proportional to x2 whole square. So if I double this, if I make it 2x2, so the rate will become the rate will, become 4 times, right? Now I'm keeping x as constant and I'm halving the concentration of y. There is no change in rate. If there is no change in rate, if I halve the concentration of y, then I can say it is y2 to the power of 0. This rate is not dependent upon y. Combining these two, we can write that rate is equal to k of x2 whole square and then y2 to the power of 0. So x2 whole square, y2 to the power of 0, that corresponds to option C. And that is the correct answer to this question. Now in this question, we have to find which graph of these quantities will produce a straight line. So our relation is between our rate constant and the temperature. So according to the Arrhenius equation, rate constant will be equal to AE to the power of minus EA by RT. Right? So obviously here, rate constant and temperature won't give us a straight line. So let's take ln or log on both sides. So ln k would be ln of A plus ln of e to the power of minus EA by RT. Because if we take log on both sides, what happens is log A, ln A plus B will be ln A plus ln B. So we'll get this. Now we'll be using another thing, that ln A to the power of B is equal to B ln A. So here I can write this thing as ln K is equal to ln A minus EA by RT times ln E. And one last concept which is required here, let's say you have log base E and E, this will be equal to 1. So ln of E is basically, ln E is basically log base E, so that is 1. So you can, we can simplify it as ln K is equal to ln A minus EA by RT. Now we can, now we can see if this can form a straight line or not. If I take ln K as y, okay, and 1 by t as x, we'll get a line which will be in the form y equals mx plus c, where your slope will be minus EA by r and your intercept or c would be ln A. So from this, ln K versus 1 by t, option D is the correct answer to this question. Moving on to the next question, we are given this reaction and the equilibrium concentration. We need to find the value of Kc. First, we will write the formula of Kc, that is ICl3 whole square divided by I2 times Cl2 whole cube. Now all these concentrations have to be taken at equilibrium for this value to be equal to Kc, and we are given the equilibrium concentrations here, so we'll just plug them inside. So ICl3 whole cube will be whole square will be 2 square. Our concentration of I2 is 0.2 and Cl2 is 0.2. So I can just write it as like this, 2 cube by 0.2 whole to the power of 4. I can make this process simpler by writing this. So simplifying this is 1 by 4 times this. So it will be, if you simplify, it will be 2500. So for question 22, option C is the correct answer to this question. Moving on to question 23. This is like a classic La-Chatelier's principle question. So we have to see which changes will shift the equilibrium to the right. First, addition of 0.01 m HCl. So addition of 0.01 m HCl will increase the Cl minus concentration by a very small amount, because 0.01 m is actually like really small. So I'm not sure if it will have a pronounced effect or not. But if we add concentrated HCl, the amount of Cl minus ion in the solution will rise, rise by a lot. And as a result, what happens is, if the amount of Cl minus rises, the reaction will try to decrease the amount of Cl minus by favoring the forward reaction. So if the forward reaction occurs, Cl minus will be used up, right? So 2 will be one of the changes which will shift the equilibrium to the right. Another one is evaporation of water. Evaporation of water is basically removing water, right? So if water is removed, by La-Chatelier's principle, the reaction will try to reverse it by producing more water, because I am removing water, the reaction will try to add more water. So that can only occur if the reaction favors the forward direction or the right direction, and in that case also H2O will be replenished and the equilibrium will shift to the right. So from all this, we can say option 2 and 3 could produce the changes. So option C, which matches with the mark scheme, but option 1 will also have a little bit effect. So the shifting won't be too much, but a little bit of the reaction will be shifted to the right. But we'll go with C. In the next question, equal volumes of 0.1 mole per dm cube. It's a weak acid and strong acid are titrated with 0.1 mole per dm cube in NaOH. Which of these are same for two acids? So if you have a weak acid and strong acid and with the same concentration, firstly the initial pH won't be the same, because weak acid will have a higher pH, strong acid will have a lower pH. So this cannot be our answer. Heat evolved in the neutralization, again it will vary upon the reaction and it will depend upon the acid. This cannot work. Volume of NaOH required for complete neutralization. This is something that can be same, because see, in both weak acid and strong acid we have equal volumes and the same concentration. So the number of moles of the weak acid and the number of moles of the strong acids are the same, right? So of weak acid this will be equal to number of moles of strong acid. So if the number of moles of weak acid and strong acid are the same, the thing is, the number of moles of NaOH, if the weak acid is like a monoprotic acid, and both the acids are monoprotic acids, then what happens is the amount of NaOH or the number of moles of NaOH that will react with each of them will be the same, because the number of moles are same, right? So if the number of moles of NaOH is the same, we can say that the volume of NaOH that would be required for complete neutralization in both the cases will be same. So from this we can say option C is the correct answer to this question. Now moving on to the next part, which species has the weakest conjugate base? So the thing is, strongest acid will have the weakest conjugate base. So here among this, H2O, HCO3 minus, these are not strong acids, these are weak acids. NH4 plus is more or less strong but not as strong as HCl. So option A is the correct answer to this question, which is HCl. For question 26, which solution will form a buffer when mixed? Now for buffer we need two conditions. We literally have just two conditions. For a buffer we either need either you have weak acid plus strong base mixture, or weak base strong acid mixture. So from this first condition we can just rule out option 1, because option A has one strong acid and one strong base. So I need either weak acid weak base or weak base strong acid. So option A will be eliminated out. And from the other options we see that it is mostly weak acid strong. All of these three are weak acid strong base mixtures. So I'll write the second condition. Second condition is our weak component must be in excess. Okay, so component must be in excess. Why so? Because see, in part B, the number of moles of NaOH will be equal to the number of moles of CH3COOH, as the volume and concentration in both the cases are the same. If the number of moles of the weak acid and the strong base are the same, so all of the reaction will go to completion, and you will have no equilibrium case to form a buffer solution. In the next one, we have less amount of CH3COOH and more amount of NaOH, right? So here also the reaction will go to completion, then there will be excess OH minus signs in the solution, but there won't be any CH3COOH to produce the buffer. But only in the last case we have more of CH3COOH and less of NaOH. So from our conditions we can say option D will be the correct answer. In option D what happens is CH3COOH can be in equilibrium with CH3COO minus. So if I add acid in this solution, CH3COO minus, the backward direction will be favored, the H plus ions will be used up, and we'll get CH3COOH. And if OH minus ions are added, or if base is added to the solution, so what happens is CH3COOH will react with this base and it will favor the forward direction, and the OH minus ions will get used up. So as a result, I can say option D can only work as a buffer solution. Now, which species can act both as a Lewis acid and Lewis base? So basically they want an amphiprotic or an amphoteric substance. So from the options we all know it's water. It's going to be water. I'll give you two examples here. So let's say if you add water to any acid, right? Let's say if you add this, I'm just showing H plus here. So what happens is water will donate its electrons to this H plus, and you will have H3O plus ion. Okay, so water donates electron here, so water acts as a base while H plus acts as an acid. Now if I have water and NH3, in this case what happens is NH3 will give its electrons to the water to form the NH4OH, which is an ionic compound, NH4OH. So in this case water is accepting electrons from NH3, so water acts as an acid while NH3 acts as a base. So we see water can act both like an acid and a base, so option A will be the correct answer to this question. Moving on to the next one, what occurs during the operation of voltaic cell based on the given reaction? So for a voltaic cell we know two things, that at anode there is oxidation and at cathode there is reduction. From the reaction we see that Cr gets oxidized and Fe2 plus gets reduced. So obviously in the anode we will have Cr to Cr3 plus, and in the cathode we will have Fe2 plus to Fe. So I'll just draw two containers here, right? This is the setup. This will be our salt bridge. Here is our this is an ammeter, right? So let's say this is a block of chromium. This is Cr3 plus, this is Fe2 plus, this is Fe, this is our salt bridge, and this is, let's say, an ammeter, right? So what happens is Cr will form Cr3 plus. So Cr will form Cr3 plus, okay, and the 3 electrons will be generated at the anode. This is the anode, this is the cathode. So the 3 electrons will be generated here, and these electrons will follow the path and move in the external circuit towards the iron. So electrons will move from Cr to Fe. We know this is correct, so any one of option A or B would be correct. Now from Fe to Fe2 plus to Fe. So what happens is Fe2 plus will accept the 2 electrons that is coming from the Ca, that's coming from the anode, and Fe2 plus will accept the 2 electrons to form Fe. So what happens is the iron bar will get thicker and thicker with time. So what happens, in order for Fe2 plus to become Fe, the Fe ions need to come closer to that of this block of iron, right? So Fe2 plus will move towards Fe. So from this I can say option B is the correct answer to this question. Now 29, this is a redox balancing question. So you have to balance the redox reaction. So I'll be using the charge balance method to solve this. So first in the charge balance method, if you know, first we'll be writing the species that are getting oxidized and reduced. We won't be discussing about H plus and H2O here. So Pb, we see Pb from oxidation number 0 becomes oxidation number plus 2, right? So here's an increase in oxidation number. N in NO3 minus has an oxidation number of, you can calculate it with this formula. Just a second, yeah. So this x minus 6 will be minus 1, so x will be plus 5. So here nitrogen has an oxidation number of plus 5. In NO, nitrogen has an oxidation number of plus 2. So oxidation number decreases in this way, it's minus 3, right? So in charge balance, we have to make the increase in oxidation number same as the decrease in oxidation number. So I can multiply this with 3 and this with 2. This will make it plus 6, this will make it minus 6. So see, the increase and decrease are the same. So I'll have to multiply, I have to make Pb as 3 Pb and NO3 minus as 2 NO3 minus and twice NO. So after charge balance, my reaction will look something like this. 2 plus plus twice NO. Now I'll balance the oxygen and hydrogen. So on the left hand side we have 6 oxygen atoms, 2 times 3, and on the right hand side we have 2 oxygen atoms. So I need to add 4 oxygen atoms to the right. So that I can do that by adding plus 4H2O, right? Now we have 8 hydrogen on the right, 0 hydrogen on the left. I can just balance that by putting 8H plus. So here we have to find the coefficients of H plus, and the coefficient of H plus is 8, or the stoichiometric coefficient of H plus is 8. That is option D. And yeah, option D is the correct answer to this question. Moving to question 30. So the standard electrode potential of 3 half cells are given. So we have to identify if Cr3 plus would be able to oxidize Cr2 plus and Cr. That is the thing. So Cr3 plus, when it acts as a reducing agent, it will have this half reaction, right? So the E0 value will be minus 0.744. There are like a lot of techniques to solve these kind of problems, but I find it most, this one as the most suitable. So first I have to check whether it can oxidize Cr or not. So the oxidation reaction of Cr is Cr would be forming Cr2 plus 2 electrons. Okay, so you might be thinking why I haven't chosen this reaction, because this reaction is same as this reaction. So if I add them together, the E0 value will come out to be as 0. But yeah, Cr3 plus, I am checking if Cr3 plus can oxidize Cr to Cr2 plus. The E0 value of this reaction, as I have reversed this, so it will be plus 0.914. So if I multiply this with 3 and this with 2, so what happens is you have twice Cr3 plus 3 Cr, giving you twice Cr plus 3 Cr2 plus. So just cancel things out, and I'll have thrice Cr2 plus, right? And the net E0 value here you will see is 0.914 minus 0.744. That is 0.7 plus 0.17 volts. So as the E0 value is positive, this reaction is possible. Cr3 plus can successfully oxidize Cr to Cr2 plus. I can say that because the net E0 value of this reaction, or the combined reaction, is positive. Now I have to check if Cr3 plus can oxidize Cr2 plus or not. So we'll just see. So again, the reaction for Cr3 plus reduction reaction would be this. E0 value will be minus 0.744. So the oxidation reaction of Cr is just Cr2 plus is just the reverse of this reaction. Cr2 plus becoming Cr3 plus electrons. So the oxidation number of Cr is changing from 2 to 3, in which you can see is getting oxidized. E0 value of this reaction, as I have flipped it, will be plus 0.407 volts. Okay. Now to balance this, I have to just multiply it with 3. So Cr3 plus thrice Cr2 plus. This will give you Cr plus thrice Cr3 plus. Okay, so I can just cancel things out and make this thrice Cr2 plus, giving you Cr plus twice Cr3 plus. So I can successfully see that Cr2 plus is getting oxidized to Cr3 plus. Yeah, and if I check the net oxidation net E0 value, it will be minus 0.744 plus 0.407, which will, if you calculate, it will be minus 0.337 volts. So the E0 value for this reaction is negative. Okay, or the E0 value of this reaction is negative. So what I can say there is that if the E0 value is negative, the reaction is not possible. Okay, or the reaction will not occur. So naturally Cr3 plus won't be able to oxidize Cr2 plus, but it will be able to oxidize Cr. So from all of this, I can say option B is the correct answer to this question. Now in this question, we have to find the factors which will affect the amount of product formed during electrolysis, and we'll be analyzing the products in moles, right? So basically we know this formula, that amount of product deposited, if I calculate it in moles, it generally has this formula, number of moles of electrons divided by charge on element, charge on the ion of the element of the element or the reactant, whichever you say, that will be correct. So from here I see that the charge on the ion is actually important. So option 1, obviously it will be within our answers, right? Now how do you get the moles of electrons? Now see, number of moles of electrons is actually time dependent. So basically charge is current times time. So the greater the time of electrolysis is, you'll have greater products deposited. So yes, so duration of electrolysis is also important. Now as we are only dealing in moles, the molar mass of the ion is not that important. So yeah, options 1 and 3 are correct, and that corresponds to option B. And the next one, which are the isomers of C5H12, which is a pretty simple question. So first we have to check if there are 5 carbon atoms in each of the structures or not. So 1, 2, 3, 4, 5 carbon atoms here. If you have an aliphatic compound, and if you have 5 carbon atoms and also there are no double or triple bonds, then you can directly use the formula of the alkene. But we can check here, 3 hydrogen here, 2 hydrogen here, that's 5. 5 3s are 8, 8 3s are 8 3s are 11, and 1 hydrogen here, so 12. So 1 is obviously an isomer. 2, 1 2 3 4 5, so there are 5 carbon atoms in 2. So 2 again, 3 hydrogen here, 3 hydrogen here, 3 hydrogen here, 3 hydrogen here, total of 12 hydrogen. So 1 and 2 are definitely isomers of C5H12. Now we'll check 3. So 1 2 3 4 5 6, it has 6 carbons, so it is not an isomer. So 1 and 2 only would be the answer, which corresponds to option A. Moving on to the next one, we have to identify which compound has a chiral carbon. So chiral carbon atom is a carbon atom with which 4 different groups are attached to it. So bromoethane, it will look like this. Obviously you can see there is no chiral carbon in this carbon atom. It's attached to 3 hydrogen. This chiral carbon is attached to 2 hydrogen and 1 CH3 and 1 Br, so obviously it's not chiral, right? Then we can talk about 2-bromopropane. Obviously you can see that this carbon atom is attached to 2 same groups, that is these 2 CH3 groups, so it is also not chiral. Now let's talk about 2-bromobutane. If we analyze this carbon atom, see, this carbon atom is attached to 1 hydrogen, 1 bromine, 1 CH3 and 1 C2H5. So obviously all the 4 groups are different, so I can say this carbon atom is a chiral carbon. And yeah, option C is the correct answer to this question. You can check option D, 3-bromopentane. So if you check here, you will see that these 2 groups are same. As a result, it is not a chiral carbon. 34. Which condition best favors oxidation of primary alcohol directly to carboxylic acid? Things first, there are 2 things here. Either we take excess acidified potassium dichromate or few drops of potassium dichromate. In this case, we have to take excess of this dichromate because there is enough amount of potassium dichromate, firstly to convert all the primary alcohols to aldehydes, and then convert the aldehydes to carboxylic acid. So excess is needed, right? Just make a point here. So all alcohol molecules could be converted to aldehyde, and all aldehyde molecules could be converted to carboxylic acid. Salicylic acid. Now there is a second thing, that is either we can do distillation or do reflux. So what is distillation? Distillation is a process which actually separates the different you can say different compounds inside a solution, right? So here we don't really need distillation, we don't need a separation process. We can do reflux, right? Because reflux is actually it's actually an act which can increase the yield of the reaction. So more of the primary alcohol would be converted to carboxylic acid. So we'll be going with reflux. Reflux is used to increase the yield of a reaction. So combining these two, obviously 34, option B is the correct answer to this question. For 35, which of the following best describes retrosynthesis? So this is just a definition based thing. So in retrosynthesis, what happens is we have a target molecule and we have an initial molecule. So we have to identify the steps which we can apply to the initial molecule to get the final molecule. In the process in the technique of retrosynthesis, we actually do a backward calculation. We start, we synthesize the target molecule by working back from the target molecule to the starting material. So obviously this is definition based or understanding based, and it's a pretty simple question. Now 36, we have to which reactants will convert nitrobenzene to phenylamine. So obviously nitrobenzene, suppose we have to reduce this nitrobenzene, right? So we need a reducing agent. Potassium dichromate is an oxidizing agent, obviously. So reducing agent is concentrated HCl and tin solid, right? This will convert this NO2 to NH3 plus. Now we need to remove the H plus ion. Remove the H plus ion, we have to put a base, okay, or a stronger base as compared to NH3 plus. I mean, yeah. So that this H plus could be removed, and if I just put OH minus, you'll get NH2 plus H2 will be as a byproduct. So combining all this, we will get option A as the correct answer to this question. Now question 37. A well-tested scientific idea which can be used to make predictions cannot explain a particular event. Which statement describes the scientific approach to this dilemma? Now, if you have a well-tested scientific idea that is used to make prediction, that is more of a theory as compared to a hypothesis, right? So we are talking about a theory here. Now, what happens if a theory could not explain a particular event? First thing is we cannot discard a theory, because a theory is a well-established explanation, okay, that has withstood rigorous testing and has a broad range of supporting evidence. So obviously we cannot discard a theory, and it's not scientifically a good idea. So obviously we should revise a theory, right? So as to include this exception within the theory. So from this, option D is the correct answer to this question. 38, we have this 2-hydrobutanoic acid that can be input to mass spectrometry, infrared spectrometry, and HNMR spectrum, right? So what information can we get? So from mass spectroscopy, so this is 2-hydroxybutanoic acid. Okay, 1 second. This is 2-hydroxybutanoic acid. So mass spectrometry will give me the molar mass of this compound. Molar mass, if you can calculate, it will be 104 grams, 104 gram per mole, right? So for mass spectrometry, there will be A or B. Infrared spectrum will tell me which functional groups are present inside this compound. So inside this compound, there are two types of functional group. One is this carboxyl group, right? Another one is this OH group. So two OH groups are present, but yeah, overall one hydroxyl and one carboxyl group is present. So IR spectrum will give me an idea about the functional groups. Just use a different color here. Groups present, right? So IR spectrometry will tell me whether it contains carboxyl or hydroxyl groups. So from just these two, we know option A will be the answer, but I can explain the HNMR spectrum too. So HNMR will basically differentiate the two OH atoms, right? It will differentiate the OH in hydroxyl and the OH in acid. So yeah, you will be able to understand that the hydroxyl group and the hydrogen is on the second and rather than the fourth carbon atom. So H1H NMR, it will tell us that OH in hydroxyl and OH in carboxylic acid are different. So option A is the correct answer to this question. Next one is the X-ray crystallography question. So X-ray crystallography gives us a 3D picture of a molecule, right? And this picture will contain all the bond lengths and the bond angles. So from the option, obviously it will be bond angles. It's pretty much a definite, it's a direct definition question. So yeah, 39 will be B. And we have the last question here, and where we have to identify which compound will have a H1 1H NMR like this. So basically you see we have three peaks. So this compound should have three different types of hydrogen. Okay. Now we have to check the option which one has three different types of hydrogen. That's it. If I take methanol will look like this. So there is only one type of hydrogen. Like these two hydrogens will be equivalent. So obviously methanol is not the answer. Ethanoic acid, CH3, COOH. So here you have two types of hydrogen. One is this type and another one is this type. So again, it's not three types. So three types of hydrogen. So obviously B is also not the answer. Ethyl ethanoate. This is ethyl ethanoate. So again, in ethyl ethanoate, we have two types of hydrogen. So that won't be the answer again. And lastly is we have propanoic acid. Propanoic acid, if we look at it, it has three types of hydrogen. 1, 2, 3. So from here, we can directly say propanoic acid will be our answer. Now we can also compare the peaks. This is the tallest peak. So obviously there is 3 hydrogen. This peak will have 2 hydrogen and this peak will have 1 hydrogen. So one environment will have 3 hydrogen atoms. The second environment will have 2 hydrogen atoms, and the third environment will have 1 hydrogen atom. You can check here 3 hydrogen, 2 hydrogen, 1 hydrogen. So from all of that, we can deduce that question 40 will be option D. So with this, we come to an end to the chemistry paper of the November 2022 attempt. I'll be posting the physics, maths, and the SL solutions as soon as possible because your exams are in May, and I hope this time we'll be able to cover all the past papers on time. Thank you so much.